Swayam Prabha. Digital India. Educated India.
Hello, welcome to this lecture. We will be discussing amplifier design and how to design an amplifier with a specified gain. First, in the beginning, we will be considering the unilateral case, and then we should be moving on to the bilateral case. So, let's see. We had discussed the unilateral case in the last lecture, and that lecture we had talked about what are the three components of unilateral gain. So just to recap, so here U means unilateral. So instead of writing GS on GL, we can use a single term GI where I can represent S or L, and it is given by this I and I is S, then II is 1 1. And if I is L, then II is 2. Okay, so so that generalizes it both for uh, S, gamma L, S11, S22 like that. Okay, because the equations will be similar for S and L when I is S or when I is L. And recall that we also had something called a maximum value of GS or GL. And I can write it like this. Okay. And we have 0, this GI, any other value of the gain will lie between the two, either 0 will lie between, so this GI will lie between 0 and GI max. Now let me define a term which I call the normalized gain. So normalized gain small g of I is given as okay, and therefore then g small gi will lie between 0 and 1. Now if we fix the value of this small gi and find the locus of gamma I for which small gi remains constant, then we'll get an equation like this. Okay, and here Ci is given like this. And this capital Ri, or sometimes I will refer to as small ri also. This capital Ri is given, so this is a vector quantity, okay? But this capital Ri, it is a scalar and its value is given by, okay? Now you can see that the centers are all located along angle of this SII conjugate. Okay, so for various values of GI, we'll get different values of CI and RI, but the centers are not concurrent. So these circles that we'll get, they are not concurrent, but the centers are located on the same line. So let's see. And note that for a certain value of gamma I, given by gamma I equal to 0, what happens? My gain Gi, if I see this equation, for gamma I equal to 0, my gain Gi is equal to 1 or 0 dB. Okay. So if we plot this, how will it look like? So I'll, instead of me drawing it, let me show you by a slide. Okay. So now we can see the slides. This is the red lines are the gain circles whose equation that I just wrote. You see that all the centers lie along this line from the origin to SII conjugate, and all the centers of all the gain circles are lie on this line joining the center to SII conjugate. Now when Gi equal to Gi max, and that happens when gamma I equal to Sii conjugate. So for Gi max circle, the radius is 0. Okay. So as the gain goes on increasing, the radius keeps on decreasing till it reaches Gi max. Okay. So this was the case when what we call it to be unconditionally stable. You might wonder that we had already discussed what is unconditionally stable earlier. Yes, we had, but there are a couple of things that are different for the unilateral case. Number one, recall how, see, for the unilateral case, if we start by the equation for gamma in, that is, this is the equation for the input reflection coefficient and the equation for the output reflection coefficient. So again, if I draw the two-port network once again, gamma out is given by, okay. But then for the unilateral case, we know that so then this implies that gamma in is simply equal to S11 and gamma out is simply equal to S22. Now recall the stability circles that we had written the equations for. They were based on gamma in as a function of gamma L is equal to 1 and gamma out as a function of gamma S is equal to 1. But then this equation will imply that modulus of S11 is equal to 1, and this equation will imply that modulus of S22 equal to 1. But then this may not always be valid, and this doesn't give me a locus of gamma L and gamma S. So then what it means is this method of determining the stability of a two-port network is not valid for the unilateral case. Okay. So let us see how to then how do we analyze the stability of a two-port network for the unilateral case. The first point is we can assume two cases. First of all, let's say S11 is magnitude of S11 is lesser than 1. Okay, if the magnitude of S11 is lesser than 1, okay, then GI max, which is given by 1 minus SII magnitude whole square, will always be positive and finite, isn't it? But if modulus of S, should have written SII is greater than 1, then GI max may be negative. So if the GI max is negative, or say if it is if GI max is negative, then it's like it's an undefined quantity, and then in that case we may not have a finite gain. And if we do not have a finite gain, then that means this represents a potentially unstable. Okay. So when GI max is positive and finite, it represents the unconditionally stable. Unconditionally stable. And when this condition is not followed, for example, this may be equal to 1, that represents a condition that is not unconditionally stable, it's potentially unstable. Okay, so for the unconditionally stable case, that is for S11 II magnitude lesser than 1, we had this mathematical treatment. Okay, this entire mathematics that we did was for the unconditionally stable case. The equation for the stability circles that we derived, that was for the unconditionally stable case. Now when it is potentially unstable, then how do we proceed? So for the potentially unstable case, we may have, first of all, we saw that this GI may be negative. Okay, and so GTU, which is equal to GS G0 GL, also may be negative. Okay, and GI, which is given by 1 minus gamma I whole square upon 1 minus SII gamma I magnitude whole square, may be infinite when SII gamma I is equal to 1. Okay, so this in turn implies that gamma I is equal to 1 upon SII, which represents a passive termination, passive value for gamma S or gamma L, because SII has a magnitude greater than 1. So then gamma I magnitude will be lesser than 1, so it will lie within the unit circle, and so then it is it represents a passive termination. So for stability, we go back to the original definition of stability, which is real part of Zi plus Zii must be greater than 0. Here Zii actually represents Z in or Z out. Okay. So then this in turn implies real part of Zi should be greater than minus real part of Zii, which is in turn equal to the magnitude of Zi, real part of Zii. Why? Because Zii must have negative real part, because Zii represents Z in, and that is equal to Sii, which itself has a Z in. So Zii, if I find out gamma in or out, that will be equal to Zii minus Z0 upon Zii plus Z0, and we know that this is equal to Sii because of the unilateral case, and since Sii has a magnitude greater than 1, so Zii must have negative real part, and which is why we can write this expression. This expression can be written as this. Okay, and how do we plot the gain plots? So for the gain plots, what we do is we keep our definition the same, except that we define our normalized gain, which we previously defined as capital GI upon GI max. Now, since we don't have anything called GI max, we substitute this with the definition of GI max, which is 1 upon 1 minus Sii magnitude whole square, which in turn comes out to be 1 minus magnitude Sii square. Okay, and GI can be negative. Okay, the locus still remains the same. The formula for the locus of constant, that is those values of gamma I for which small gi is constant. The definition also of Ci and Ri also remains the same. So Ci is given by so the formulae for Ci and Ri remain the same as that for the unconditionally stable case. The only problem that a designer might face is how to locate this point. So as you might recall, for the unconditionally stable case, all the centers of all the constant gain circles lied along the line joining the origin and this point. But then because magnitude Sii is greater than 1, this point lies outside the unit circle. And on a Smith chart, it's very difficult to plot any impedance that is outside the unit circle. So the way to do it is that you first draw a line joining origin to 1 upon Sii. So the 1 upon Sii point, which will lie within the unit circle if magnitude Sii is greater than 1, now this point has the same phase or same argument as this point, and so the center of all the constant gain circles will lie along the line joining the origin and this point. So that's how you plot. So again, you might still have a point where gi is equal to 1. This happens for gamma I equal to 0. So this condition remains the same as that for the unconditionally stable case. So let me once again share my slides. So you can see that these purple lines. They represent the constant gain circles, these lines, for the potentially unstable case. Now, as I mentioned, the center of all these circles lie on the same straight line joining the origin with this point 1 upon S11. These circles are not concentric, and in order to satisfy this condition, which was that the real part of Zi must be greater than the magnitude of the real part of Zii. So that is represented by these two circles, this white circle and this pink circle. So suppose real part of Zii, okay, Zii represents the input impedance or the output impedance. So say the magnitude of real part of Zii is this point, then for real values of Zi greater than real values of Zii given by this equation, the gain will be stable. So which are the points on this gamma I plane which satisfy this equation? So those values will be represented by this white circle. It's just that the real part, those impedances for which the real part of Zi is greater than real part of Zii. So real part of Zii is this point. So the impedances for which the real part will be, or those values, or let me put it in a different way, those values of Zii whose real part is greater than this value will be represented by this white circle. So that's how we come to determine which is the stable region and which is the unstable region. This is a lot different from those gains from the stability circles we discussed in the last lecture. Okay, I hope it is clear. Okay. So the next topic, I'll continue my discussion on this slide itself. Suppose, let's go back to this slide for a moment. Now in this slide, suppose I want to obtain a gain as given by this largest purple circle. So I have to choose the point which is most stable. So which is that point? The point on this purple circle which is farthest from this boundary between the unstable and stable region will be the most stable, and that point is nothing but the point of intersection of this purple line with a constant resistance circle which is just touching this purple line. Say I call that gamma s. Now I have to say this is my gamma s plane now. Okay, let me just instead of calling it gamma I, which makes it vague whether it refers to gamma s or gamma s. Say now this is my gamma s plane. The same treatment will happen for the gamma L plane. So I have to design an impedance matching network that will take me, say whatever is my source impedance to this gamma s value. Let's come to this slide now. So this shows the setup of how I will be performing the impedance matching. So here my source impedance is 50 ohms and I have to bring it to gamma s. So source impedance 50 ohm means that is the origin of the unit of this gamma s plane, which represents this point A, and I have to go to this point gamma s. So this is the path I take. First I go along a constant conductance circle, and then that I call path A. So A represents a path, not a point. And B, and then after reaching this point, I take a constant resistance circle. So the constant resistance circle where I intersect my constant conductance circle will correspond to the constant resistance circle passing through the gamma S point. Okay, so since I am traveling first along a constant conductance circle downwards, that is the path A, I have this capacitor C, and then after reaching this point, I am going upwards along a constant resistance circle, path B, and that is represented by this inductor. That's how I obtain my impedance matching network. I could have done it this way also. So this represents the second scenario, how I can obtain the same matching network. So here, instead of first traveling downwards along a constant conductance circle, I first travel upwards along a constant resistance circle, path A, and then I go upwards along a constant conductance circle. So going upwards along a constant resistance circle represents a series inductance. Okay, and then again going upwards along a constant conductance circle represents a shunt inductance. Okay, so these are various cases. These are given in the slides, and I will expect you to go through this yourself. Okay, so let me go on to the next topic now. So there is, we now there is a how valid is this unilateral approximation that we have made? We have this entire design procedure that I showed is for the unilateral case, isn't it? And for the unilateral case, what it means is that we consider S12 to be 0. Now the question is this a valid approximation? So to understand whether it's a valid approximation or not, let us let us see the ratio of the gain obtained for the unilateral case with that obtained for the bilateral case. So for the bilateral case, and once again, the gain that we are discussing for all these discussions is the transducer gain, GT. We are only discussing the unilateral case for the transducer gain. We can have the unilateral case only for the transducer gain, okay, not for the other gains like GP and GA. As we shall see in a few minutes, we can have design constant gain circles for GP and GA also, but not for the bilateral transducer gain. We can have gain circles for the GS and GL, that is the unilateral transducer gain case, but not for the bilateral gain case. So the formula for GT is given like this. And GTU we call is given like this. So now if I take this ratio GT on GTU, I will get an expression like this. I would like you to derive this expression. So then the maximum and minimum values of this ratio is given by okay. Now instead of GTU, if we use GTU max, so we have GTU max for and say uh, we now evaluate this condition. What we get is okay. So whatever the value of ux that you choose, let me write the expression. I didn't write the expression for ux. Ux is given by so whatever the value of ux is, okay, that our gt upon gtu max will be between these two values. So that gives us an idea how good our unilateral figure of merit is. If depending on the values of the s parameters, that is the value of ux, so how close gt is to gtu max will depend on how close uh, will depend on what the value of ux is. So for example, for the case when not s21, say for the case when really our s12 is equal to 0, then in that case ux will be equal to 0 and gt will be equal to gtu max. But if suppose s12 is not equal to 0, still then if ux is very small, say, then our gt will be very close to gtu max. Okay. So this was the unilateral case. For the bilateral case, we can't have a design as such, the way we have designed it. We can't have that. Instead, but we can have one case, that is if both the ports are well matched. So then that gives the case for the maximum value of GT. So for the bilateral case, let's see. Okay. So for this case, this recall the condition that we have to satisfy, that is gamma S is equal to gamma in conjugate, and gamma in itself is a function of gamma L, and gamma L is equal to gamma out conjugate, and gamma out conjugate is a function of gamma S. Now this represents two linear equations, isn't it? Because recall gamma in is equal to S11 plus S12 gamma L S21 upon 1 minus, let me just confirm, 1 minus S22 gamma L. Okay, so this is the formula for gamma in. So similarly, we can write the formula for gamma out, and what we will get. So you see, gamma in is a function of gamma L. So if we plug this whole equation into this equation, the first one, we get one relation between gamma S and gamma L, and from this equation, we'll get a second linear equation relating gamma L to gamma S. And if we solve both the equations, okay, what we will get is the optimum value of gamma S and gamma L, for which these two equations are satisfied, and that optimum value of gamma S and gamma L, which I call gamma MS and gamma ML, are given like this. Okay, and the value of GT when these two conditions are satisfied, okay, that is when these two conditions are satisfied, we are supposed to get the maximum value of GT, and recall that is GT max. This we have discussed earlier also, and we have said that GT max is equal to GP max, which is in turn equal to GA max, and the value of this is given by this capital K is nothing but that constant, that parameter K, which we discussed while discussing stability. So K is equal to 1 minus so this equation shows why that K should be greater than 1, because GT max, which is a real quantity, is obtainable only when this quantity is real, and that for that to happen, K should be greater than 1. Now for, so K greater than 1 and Recall the condition for stability: mod delta should be lesser than 1, k should be greater than 1. This represents the unconditional stability case. So when the system is unconditionally stable, we do have the definition of GT max, right? Uh, that means the gain, maximum gain that can be obtained is finite, and therefore the system is stable. But for the potentially unstable case, GT max may not be finite. The maximum value of, if the system is unstable, the value of GT max can be infinite. So, uh, so for the potentially unstable case, since we cannot define GT max, what we do is we define something called MSG, maximum stable gain. So MSG, and this is given by modulus of S21 upon S12, which is equal to the, basically what we are doing here is we are just plugging k equal to 1, okay, in this equation. You just plug k equal to 1. The reasoning being k equal to, if k is greater than 1, then the system is stable. If k is lesser than 1, the system is potentially unstable. So k equal to 1 represents the boundary between instability and stability, and by plugging k equal to 1, we get the value of GT max as S21 and S12, the ratio, this value, and that we call the maximum stable gain. It's like, even though the system is potentially unstable, had the system been stable, what would be the maximum gain obtainable? Now this quantity GT max, recall, is also equal to GP max and is equal to GA max. That's why this quantity is also called maximum available gain, or MAG. Now both this MAG and MSG are important parameters for any microwave transistor. In the data sheet for any of these transistors, you will find these values given. Okay, so the reason why it is given is because if we plot this GT max with frequency, now for higher frequencies the system is more stable, and that's why we can define MAG for higher frequency. But for lower frequencies, where the system is more likely to be unstable, instead of defining MAG, we define the MSG. Usually it is a 10 dB per decade curve, whereas the MAG is a 20 dB per decade curve. Now the frequency where GT max becomes 1, if we go on seeing the value of MAG, and for a certain value called F max, the value of GT max will be unity. So at this frequency, the transistor no longer acts like an active device, it becomes a passive device. This is called F max and is another important parameter of any microwave transistor. This is in log F. This is in dB. Now, even though for the potentially unstable case, we cannot define uh, anything called the maximum gain. For one particular case, when k is greater than 1 and mod delta is greater than 1, okay, so this also represents a potentially unstable case, because k, even though k is greater than 1, but mod delta is also greater than 1. So for this particular case, we can define something called a GT min, or the minimum transducer gain, and that is given as now. There is also something called F min that I will discuss in a later lecture. Okay, so that was all about MAG. So what are some of the important parameters that we saw for any microwave transistor? One is MAG, MSG, Fmax. And the relation between all the parameters is given by this graph. Okay. Now the next important uh, design tool or design methodology that we have is designing using the constant GP circles. So this entire procedure that we discussed was first for the unilateral case. We tried to find out the constant gain circles both for gamma S plane and the gamma L plane, and then we found out the methodology to find out GT max for the bilateral case, and now we are trying to design using the GP circles, or the constant power gain circles. So just like the unilateral transducer gain case, when GP is constant, we can define small gp or normalized gp as capital GP upon 1 by S21. Okay, so this is the normalized power gain, and if this is true, then the locus of gamma L, for which the value of GP is constant, is given by this equation, where Cp represents the center of the circle and Rp represents the radius, and the value of Cp is given by so this is a very long expression. It's given in your notes, um, and as you can see that now the C2 identifying what is the C2 is given by S22 minus delta S11 conjugate. As you can see, the C2 is constant. That is, as long as the S parameters are constant, the value of C2 is constant. So again, all the constant GP circles will lie on the same straight line. Okay. When gamma L, when this gamma L gamma L is the value that we derived a few minutes back. Then we obtained Gp equal to Gp max, which in turn is equal to Gt max, which in turn is equal to Ga max. But you see that using the Gp circles, we only get a value of gamma L, okay, not gamma S. So let me show you how the design procedure for design using gamma GP will be. So you see these red lines here on this slide represents the constant GP circles, and this blue circle is our unit circle of the Smith chart. This is the gamma L plane. So suppose you want a certain gain, say this line. This line represents the constant gain circle. This circle rather represents the constant gain circle for a certain gain. You choose the value of gamma L at any points. Okay. Then once you choose that value of gamma L, you choose the value of gamma S as per this equation. Gamma S is equal to gamma in conjugate. So you first choose gamma L, calculate the value of gamma in, and then set your gamma S according to this equation. Okay. So suppose you also have your output stability circle present. So this slide shows what happens when both your constant GP circles as well as your output stability circle is present. In this case, you choose and suppose say this red circle represents the gain that you wish to achieve. So you cannot choose a point which lies in the potentially unstable region. You have to choose a point which is first of all inside the unit circle and also outside this potentially unstable region. Okay. Uh, so that's how we can design it. But there is one more check you need to do. So we select our gamma S as per this equation, gamma S equal to gamma in conjugate. But we now need to check whether this gamma S lies in the stable region of the input stability circle. Okay. So this represents the output stability circle with the constant GP circles. We choose a value of gamma L. Okay, we then find out gamma in and set gamma S as per this equation. Then we draw the input stability circle, okay, and see whether gamma S lies in the stable region or not. If not, then we have to redo the whole process. That is, we go back to this diagram, okay. We select a value of gamma L which is again in the stable region but different from the previous one. Again find out the value of gamma in, again choose gamma S as per this equation, and then again go back to the input stability circles on the gamma S plane to check whether this value of gamma S that we are setting lies in the stable region or not. Okay, so we have to keep on doing this till we reach a point where both our gamma S and gamma L lie in the respective stable regions. Now, the design using constant available gain circles is similar to the procedure for design using constant GP circles, except that in the case of constant available GA circles or constant available power gain circles, So these are the equations for the constant of GA circles. It's, as I said, in microwave engineering, especially for two-port networks, you'll find dual expressions. So this available power gain circles are the dual of the GP circles. So this represents the available gain circles for the unconditionally stable case. So here we have drawn the available power circles, these red lines. CA represents the circle for maximum available power gain, or MAG, and at when the maximum available power gain is obtained, or my gamma S is equal to gamma MS. So here I first choose the value of gamma L, then find out the value of gamma out and set my gamma L is equal to gamma out conjugate. So if I have a potentially unstable case, I again choose the value of gamma S that lies in the stable region. I find out gamma out and set my gamma L equal to gamma out conjugate, and then go back to the output stability circle. So this was my input stability circle. It's just the converse of what I did for GP circles. I go back to my output stability circles and check whether this value of gamma L that I have set itself lies in the stable region or not. Okay? So it's just the converse of the design methodology that I described used for the GP circles. So with that, I come to an end to this part. Thank you.